Great. So for homework 6, as some of you mentioned, or a few of you had a hard time reading the example questions towards the end. The grader graded it without having if you were missing some of the examples. So since you pretty much need to do the examples anyway to study for your exam coming up here on Tuesday, for those of you who weren't able to do the examples, we did all of those examples in the next lecture. So you can take that opportunity to do it over the weekend, and you can submit that on Tuesday. If you missed the examples on homework 6, you can submit them on Tuesday for full credit to get the credit back. Now for homework 7, since for today's homework, it's going to be homework 8. I wanted to make a note here that homework 8 will be due next Thursday. Since nothing we're covering in class day is going to be on the exam, I don't want you worrying about it. Get that, focus on your exam, and then have the homework so that way when we come in on Thursday, you'll have the stuff that we've done in chapter 3 taken care of. So did I have everybody's homework 7? I need to press. So now that homework's handed back. So let me ask you, what do you think will be on the exam? TGO's what? TGO's, I don't know. Computer architecture and organization. Right? Define and differentiate between computer architecture and computer organization. Yep. Define digital system. Amdahl's law. Amdahl's law. The CPI and instructions. And the speed up. You'll be asked to do a performance-based question. Right? Just like similar to quiz 1, which the solution's on Blackboard. What else?
Race conditions.
Race conditions. So you want to do so K-maps, you got race conditions. What else what type of question did I say you can expect about using K-maps? So similar to example 2.6, what was the difference that I said would be between that question and the one you'll have on the exam? So remember on the question I asked you to scan an expansion about each of the inputs and then select which one. To reduce the amount of time on the exam to make sure the question is fair, I'm going to give you a variable to do the Shannon expansion around. So it's going to be a 3-variable question, A, B, C. And let's say I say do the Shannon expansion about variable B. What does that mean?
Calculate the costs and do the total cost and then draw the circle.
Right. So when I have 2 to 1 mux, right? So if I say Shannon expansion about B, what does that imply about the multiplexer? B is going to be exactly right. B will be the select value. And then you're going to calculate the input cost for the function of A and for the function of C, right? So you would do the K-map how? Yeah, B is going to be your 0 and 1 variable, and in AC would be your 0, 0, 0, 1, 1, 1, 1, 0. So that's where, remember we were talking about gray code? That's where we're going to test your knowledge to properly do the gray code for both for the Shannon expansion. And then you would do the cost calculation. And why don't we account, so let's say it's going to be B not A or C, and then B, A, and C. Let's say those are our functions that we derive. What would be the, so what's the literal cost for A or C? 2. And what's the A cost? 2. Yeah, why is it not 1? C, exactly right. I've never made mistakes now on the exam. And so what's my inverter cost? 0. So what's the total cost for the B map? 4, exactly right. And so if it's A and B, what's my literal cost? What's my gate cost? 1. Because they're together. It's a 1 gate. They're smushed together. They're separated by an OR. That means OR is further cost on input. So we have 2, 1, and what's my inverter cost? 0. So if I have 4 and 3, what's my total cost? 7. 4 plus 1 is 2 plus 1 is 3. Yeah. So it's going to be 7. So why am I not counting the B map and gate? Yeah, because that's what the multiplex is going to be, right? So you don't have to worry about that. So, and then the last thing you do is show me how to draw AND and OR gates to the input to the 2 to 1 box. So that's what the question is going to be. Because due to time, I'm not going to have you do a comparison, but it's good to do that 2.6, practice that problem, because you'll see why you want to do Shannon expansion about all 3 variables. Why would we? For those of you now that you know Vhdl and you know how much of a pain in the butt it is to deal with larger gates, what's the advantage of doing lower costs for Shannon expansion? Less code, less time in the teaching class, right? So that's the reason I taught that, to show you guys, because you shouldn't just be like just going in there doing the assignment. I mean, a lot of you guys, when you're asking me questions, and lady, when you're asking me questions, you'd say, okay, so I have a 16 to 1 mux, right? And can I do it with 4 to 1 muxes? Yeah. If you can do code reuse to reduce the amount of work you have to do, that's good. That shows me that you are engineering. And since you want to be electrical engineers, that's your job description. So, okay, so example similar to 2.6, you're going to be doing the K-map, determining input cost, and then drawing the circuit. K-map for Shannon expansion. What else can I ask on this exam?
Vhdl.
Yep, so VHDL. What exactly would I be asking about the VHDL?
Library.
Make sure you include there's the 2 libraries. What are the 2 things that you have to include at the top of every?
Library IEEE.
Library IEEE, and then
1164.
Yep, use IEEE standard logic 64.all, right?
754.
1164.
1164. No.
No, use 1164.
Okay.
If you put 754, you lose points.
Yeah, I'm saying, will you ask anything about 754?
No. That's okay. So that's the IEEE 754 is a standard specifically for the floating point calculation.
You won't ask the same thing.
No, that's not a VHDL standard. That's an architecture standard.
Oh, okay.
No, that will be on your next exam. They'll be limited to section 1 and 2. So library. What else could I ask?
The code for
Code.
for a tri-state buffer or a tri-state.
So how did I tell you I would phrase the question? I have it in 2 parts. Part 1 was what? Since you guys have. So if I'm asking you to write the code for a tri-state buffer or a tri-state inverter, what's the first thing I'd want to ask you? As a professor, it is my job to determine, what is a tri-state buffer, right? What is a tri-state buffer or inverter? And then be able to draw the truth table, right? And then part 2 would be write a structural VHDL entity architecture pair. Sure, but also bear in mind it's on video, so we're also going to, write a structural VHDL entity architecture pair for whatever one I ask you for. And I will also have a little note on the exam to include the library so you don't forget.
No, the architecture pair, we don't email them.
It'll be, I pretty much limited it to tri-state buffer, tri-state inverter, or 2-to-1 mux.
Now are you going to give us the option to do one of those?
No, you will be required to do the one I ask.
Okay.
Yeah, that's better. I have to keep the sanity of my grader in mind. Okay, what else? Okay, so I originally was doing plan on doing section 1 through section 3 on the exam. We got through section 2 because I adapted for Vhdl help. So there are a couple things I wanted to add here because once you've practiced this problem, you'll realize it should, doing this should take you about 10 minutes or so. The performance question should take you 15 minutes. So I want to add one other thing, or two other brief things that could potentially be on the exam. Remember when we were doing Mealy and Moore machines, and I gave you a machine and I asked you to be able to do the input and output? I'll give you a starting state, a machine, and I'm going to want you to do the input and output. So there are 2 practice problems on those. So I could give you a Mealy or a Moore machine, and then show input and output. And then I'm going to ask you one of the 2 following things. I'm still deciding. Maybe they're going to ask you to tell me the basic philosophy of MIPS. Right? Remember that topical guide objective? And then I'm going to ask you to tell me the difference between behavioral and structural, physical VHDL. Remember that's a TGO as well? No, that's not the diagram. There's 3 definitions: behavioral, structural, and VHDL. I believe that was I forget which TGO it was. So these are the 2 things I added because we haven't gotten enough into section 3 yet, so that I feel comfortable asking about it on the exam, which answers your question about 754. Other than it exists. Yeah. This is true. Okay. So, make sure. Performance.
Modeling, structural modeling.
Yeah.
That's 2.2.
Yeah. Mm-hmm. That's TGO 2.2. So this type of question and these questions here are, do you know fundamental concepts? And then you're going to take these fundamental concepts. Also, you've done a lot of TGOs on performance, but you know how they build up to being able to show mastery learning and that you understand how to use it. Again, all of this is building up to, can you use K-maps and your understanding of multiplexers to be able to design a reduced circuit, and then write some VHDL code. So this will be the only time I ask about VHDL code on an exam. I just want to know that everybody at least has a cursory understanding of it. This is partially so I know you know it, and partially so that way people can't just skate by and have the other people in their groups write all the VHDL code for them. So at some point, everybody needs to demonstrate that they know it. Yes?
Are there performance-based questions like in the book that you
Yeah, and there are a lot of performance-based questions in the Patterson-Hennessy textbook in chapter 2. Chapter 2 is filled with them, filled with good examples. If you can do all the examples, you'll be able to do the exam question.
Does it include answers to those questions?
Yeah, the ones, the examples, they have answers. For those of you who don't have the textbook, the questions that we did in class, a lot of them are the same examples, but then I built on some of them, and the quiz question if you know the quiz question, you can do the quiz question. And a good way to practice is to change the numbers in the CPI. If you understand average CPI, and being able to take an average CPI. So we can look. Let's go into Blackboard here for a split second. If we have internet, which we don't.
Before you go on with this, the code that we're supposed to write on the Vhdl for other derivatives.
Mm-hmm.
If we just miss something like end or end behavior, or if I put something in the wrong place, how much will that count off?
What do you mean, like
for syntax?
Oh, you mean for performance-based question or for what?
For the
Just make sure that.
Because I don't really, you know.
Well, good. This weekend's a good weekend of practice. So let's get the performance-based question. I mean, you should be able to the syntax. I mean, it's right structural VHDL code, so you should understand the syntax and how it works.
All right. Because it'll count off full marks if I.
Oh, no. I mean, if you miss a semicolon, I'm not going to hammer you too hard. I mean, the key thing is you should show me that you understand the libraries. You should show me you understand what is an entity, what is an architecture, how do if statements work. So if you're doing a tri-state buffer, right, and I say, all right, so I have entity tri-state buffer, and I know the inputs. So I have A and the enable signal as in STD logic, and F as out STD logic. So you can show me how to build an entity, right? That's the key part. And then going to the architecture process, if enable equals 1, if enable equals 1, then F is maps to A. Then else output what? What do we output? For a tri-state buffer. If the enable signal is equal to 0, what are we outputting?
For a tri-state buffer, C?
Yeah, C, right? So high impedance. So if you can do that, then you're good. I'm going to masterfully type while looking at the professor too. Okay, so here's the, so this quiz key is posted to Blackboard. So we had a set of CPI instructions, so I can bring up the, is that there too? Oh no, that's just the Word document. So the quiz 1. So if you recall from quiz 1, if the computer can recall from quiz 1 too, it's like, nope, don't want to. Okay, so if first you don't succeed, try again. Come on. There we go. All right, so we had load, store, arithmetic, branch, and jump, right, for the performance is what I was just being asked about. So you want to practice, you can do calculate average CPI. And how do we calculate the average CPI given this table? What's average CPI? Oh, cycles per section is CPI. What is average CPI? Yeah, so more specifically, the sum of what? What's in the numerator? The sum of number of instructions times CPI for each individual one. And then what's in the denominator? Number of instructions. That was a common mistake. You would multiply these correctly, and in the denominator you add 3 plus 2 plus 1 plus 2. So don't do that. So in this case, let's derive this equation together. What's in the numerator? Yeah, so 10 times 3 plus 5 times 2. So now what's in the denominator? 10 plus 50 plus 10 plus 5. All right, and we look at our answer key, and it's exactly right. And then you can see, I'll definitely do the same thing where if you're juniors and seniors or a couple cases freshmen in college, you should be able to know what 10 times 3 is. So the numbers are going to come out, and you're going to see that if you get some sort of weird thing like it's 110 divided by 86, you're probably on the wrong. You made a mistake somewhere. Oh, and by the way, my policy on exam is I won't be able to tell you exactly where you made your mistake, but if you come up to me, I'll be able to say, take a look at that again. Specifically, look around here. Yeah, that's the kind of things that I can do as a professor on your exam, just to make sure that you're towards the right space. So, okay, so now we have, so remember our average CPI was 2. That we just calculated because it's 150 divided by 75. So now we have the execution time of the program. How do we do that?
Execution time is seconds over.
What's the yes? Oh no. What's execution time? Well, think about it. What is it called? It's execution time, right?
Oh, so it's seconds.
Yeah, just seconds, right? So if I'm asking for execution time, I want seconds as my final unit. So what are the things that I have? I have 2 gigahertz. What's gigahertz? Cycles per second, right? So a good thing to do is to go, I have cycles per second. And what do we have here? What else do we have?
Cycles per instruction.
Cycles per instruction, right? And so what else do I have? I have number of instructions, right? So now, without even knowing the equation, I can say, well, I want to end at seconds, right? So I want to do, what would I want to do here next?
Instructions, cycles,
Instruction. Hold on, I see what you're trying to do, and I'm going to go to a different route. I understand what you're trying to do, though. I'll explain what you're doing there in a second. So, if I have seconds, what do I want to do next? Why would I do? What does cycles over second match the units? No. So if I want to start with seconds, the first thing I want to do is what's my seconds unit? Seconds over cycles. So this becomes, that's going to be, when we get down here, it's going to be 1 over the clock rate, right?
Mm-hmm.
So now I somehow have to get rid of cycles, right? Yep, cycles per instruction, because this will cancel out. So now we've canceled these out. And well, instructions won't get rid of itself. How do we get rid of it? Times instruction, right? So now you've derived the equation without knowing the actual thing from the TGO. Now, you knew the definition from the TGOs, which is what you were saying. So what he was saying was the cycle time was instructions times CPI divided by cycle time, which is the same thing as what we just derived. So now that we have our equation, clock rate times CPI times number of instructions. So what are our numbers for this? (10 to the 9), right? Times, yeah, -9. No, it's number 9. Yeah, because if you made this -9, what's going to happen to our final solution? It's going to invert. So it's your execution time is going to be something times 10 to the 9, which is, you're going to be dead by the time the program finishes. It's finally done. All I really want to do is just do stupid Vhdls. Yeah, I think will never finish. So what was CPI? 2. Yeah, you already calculated. And what was the number of instructions? 75, right? And we got that by doing 10 plus 50 plus 10 plus 5. And so this becomes 150 over 2 times 10 to the -9. I'm sorry, 2 times 10 to the 9. Right, so this is all in the denominator, which becomes 75 times 10 to the -9 seconds, which is what you got. Okay, so part C is what happens. We have 2 engineers. One of them says, I can increase my clock rate from 2 to 2.5. And the second one says, I can reduce the CPI of arithmetic from 2 to 1. Which improvement is better? And by how much? Or if you just put B, you don't have an answer, no work, no credit. And so how do we do this? So for the first engineer, what you can do is you can just take this work that you've already done, right? You want to try to, so instead of doing 2, you just do 2.5. This becomes 50 divided by 2.5, which becomes 60. So that means like 225 to 150 divided by 25 is 6, right? So you do the decimal, it just becomes 60. So now, if you had second engineer, we're going to come by and we're going to say, do the same thing. 50 times, you've already done the 50 times 3 plus, 10 times 3 plus 50 times 2. So we already know that the numerator is 150, right? Divided by 75 for the first calculation. So this was, if you take this, you have 50 times 2, so that was 100 out of the 150, right? So this just becomes 50 plus, and this is where Amdahl's law comes into play, so this becomes 50 times 1 instead of 50 times 2, right? So that just becomes 100 over 75. And then if you do the second part, this would become, instead of 150, this just becomes 100 over 2, which becomes 50 times 10 to the negative 9, right? So which one? So now we know the execution times for both of the programs. So performance, if you recall, whenever I ask which proposed improvement is better, you do performance, right? A over, so this would be, we'll call this performance A over performance B is equal to what? Exactly right. Execution time B over execution time A, which we can call 60 over 50, 6/5. So we can say that, I'm sorry, we'll call this 50 over 60, since we'll call this one A, and we'll call this one B. So since it's less than 1, what does that mean?
Faster.
Which one's faster? Yep. Therefore, B is faster. Does that make sense now? All right. There you go. So this one, the only difference is I did performance 2 over performance 1 is execution time 1 over execution times 2. So I got the inversion there. And since it was greater than 1, that means the one in the denominator is better. And since you got less than 1 here, that means the one in the numerator is better, which meant B. And let me get rid of all that. Okay, does anybody have any additional questions before we move on? So,
yes, sir. Considering the other TGOs that we didn't discuss off this list, would you say just look over them and not put as much of emphasis on?
Right. Well, yeah. So a lot of these questions are building chunks of TGOs. Like the performance question is a huge collection of TGOs building up towards being able to demonstrate understanding through correct application of the question. Same thing for this question with the Shannon expansion. Everything that we did with K-maps, everything we did with race conditions, everything we did with multiplexers, everything we did with input costs is all in one small question. Vhdl, we did this whole section on Vhdl. So a lot of the TGOs kind of come into this. So basically, your exam is going to be a subset of this, what we have here. So you guys were pretty well prepared, I'd say. You guys knew what was coming. So you did a very good job of your review. Very good. Good job, guys. If it's not, it's going to be some subset. So if it's not on this list, it will not be on the exam. That's what I mean by that. So anything in section 3 will not be covered. It's going to be section 1 and section 2 only. That's it. A little little fist pound there.
Freed up the weekend a little bit, thank you.
Yep. All right. So the next thing I want to cover is some basics of computing arithmetic. Now, we were just talking about the IEEE 754 standard. So IEEE 1164 standard was the standard for multi-value logic when implementing Vhdl. The IEEE comes up with standards for everything from coding Vhdl to doing things at the arithmetic level. And this is an example. Remember last class we were talking about sign bit, exponent, and mantissa? So what is, so hold on, I can, uh-oh, it's gone. Okay, so what is each of these, so I have these two questions here, right? I have these part A and part B. I just wanted you to show me you understand. So what does the IEEE 754 standard, what is that actually doing? Why are we using it?
It's using that. That formula.
Mm-hmm.
That
Remember? Exactly right. You're kind of
H2 to the negative, or it was -1 to the S times 1 plus the mantissa, and then times 2 to the some power minus 127.
Bingo. Exactly right. Exactly straight from the TGI. And our mantissa, we calculate by doing. We still have to bully the students to get the question correct. It wasn't bullying, but of course I'm so but the idea is that you have the -1 to the exponent. So -1 to 0 is what? No. 1, right? Anything to the 0th power is automatically 1. So that's how this part of the equation, if you recall from last class, this is what you just recited. And so 1 plus the mantissa. Remember we assumed that it's 1 point something, right? And that's assumed in the standard. And so that's the mantissa, which you were just asking about earlier. Or as one student once put on an exam, the Medusa. I was like, whatever, that's not what I asked, but sure. And this part's the exponent. So why did we do the base where we have this so if I have 8 bits, right, what can I represent up to? You're doing you're answering part A, you're answering the next part of my question. So you're up to 256, so 0 to 255, right? And then the offset of the equation becomes 255 minus 127, right? So that's the maximum, so that becomes what? 128. And then what's our minimum value? When that value is 0, it becomes negative 127. So if we drew an unsigned bit where we have 32 bits, it just becomes up to 2 to the 31, 2 to the 32 minus 1, right? We have signed bit, that means that first bit represents a sign, so it becomes 2 to the 31 minus 1, right? So what happens when we want to go past that? We want to go past 0 and to the 31st, right? We want to actually represent negative exponents or past 2 to the 31st. We use this value here, where in this case, since it's 255, right? Since it's all ones and it's all zeros, what does that actually mean? Since we now know the equation. Negative infinity, right? So our first line here, bring it back. So the calculation becomes, I'll bring this up to the top for those of you in the back. -1 to the 1, so that goes negative 1 plus 0. I say it's 0 because it's all zeros. Now, I should note, on any question on the exam, I'm not going to put anything past these first 4 bits in terms of doing a calculation because there's only so much time and I can ask you only so much, right? I've seen professors do things where they're calculating floating point addition. It's got to carry over and over and over, right? That's nasty. We're not going to do that. And a waste of time and doesn't demonstrate any knowledge. So then it becomes 255 minus 127, as you guys said. So now we have negative 2 to the 128, which in the standard is defined as negative infinity. So now we have this one here. This one is not negative infinity, right? So what is this value? So let's calculate the value. So what does this bit mean? Positive, right? So that's correct? So let me get. So now what are we doing here? So if we have 0, 1, 0, 1 here, right? What does this mean with the mantissa?
2 to the 21 plus 2 to the...
No. We're just talking about the mantissa. We're going to get to the exponent here in a minute. So these bits, what does this actually mean? When I say that the mantissa is 1 plus this value, one plus 0.0101. That's what that means. So how many of you know what this, so now this becomes 1.0101. So what is this in decimal? What is that? I'm going to show you a little trick for those of you who don't know.
That's 4.
What's that?
0, 1, 0, 1's 4.
No. It's after the decimal, right?
Yeah.
Yes, you're going, trust yourself. Do it. It's negative, right?
Yeah. 2 to the negative 1.
Bingo. Exactly right. So 2 to the negative 1 is what? 1 over 2 is what? 0.5. And it's a 0. So do we add that? What's so it's the next one is 2 to the negative 2, right? So that's what? 1 over 4 is what? So this is going to be 1 plus, because we have 1 here, right? So this becomes plus 0.25. So what's 1 over 8? It's going to be 1/2 of 0.25, which is, bingo, 0.125. So do we add that here? So that's nothing. And then what's this last one? Yeah, so which is 0.625. And that's going to be equal to 1.3125. Which, we would just select that part.
So the mantissa is that decimal? It's just
Yes, the man.
put 0 point and then
1 point.
Oh, yeah, 1 point.
1 point, and then it goes from there.
We're gonna do the first 4 bits.
So here's the trick, and this is something so what I'll do is you'll get this is something that's useful for the first 4 bits, right? So where we said 2 to the negative 1, no, bad. 2 to the negative 1 is equal to what? 1/2, right? Yeah. Which we said is equal to 0.5, right? So let's go 1 over 2 to the negative 2 is what? 1/4, which is equal to 0.25. So copy all this again. Hopefully I won't have to do the re. So 2 negative 3 is what? 1 over 8, which is going to be 1/2 of 0.25, right? So this becomes 0.125. And then last but certainly not least, the 4 bits is 1/16, which becomes 0.0625. So oftentimes I'll see students when you guys are doing exam 2 and you'll be required to do floating point addition problem. They'll actually write these 4 numbers out when they get to the question. So that way they know that I'm only going to ask the first 4 bits. So that they can do the calculations in this way. And this is how to derive those numbers. So if I gave you, let's test to see how well you guys understand this. If I gave you 1.1011, how do we calculate this? 1 plus
0.125.
Bingo, that's exactly right. So that becomes 0.625 here. And you guys will be able to put this into a calculator. So, but this becomes 0.825 1.6875. Right? So there you go. Now you guys know how to do it. Okay, so now that we figured this part out,
Where did the exponents come from one more time?
yeah, that's what we're going to do next. So we have times. You're on top of it. And so what is this number here?
Okay.
So this is the exponent value in the so if I have an 8-bit and this is the most significant bit is 1, right? What does that mean?
The last 4 bits.
Yeah, 128, right? Yeah. 128, and what's this value here? 5. So what's 128 plus 5? 133. Yep. So that becomes 133 minus 127. Okay, so now that becomes 1.3125 times 2 to the 6, which I've taken the liberty of doing the rest of that for you, which is equal to 84. So does this make sense how you calculated this out? So on your second exam, you can expect a problem similar to this, where I'll ask you to demonstrate one of the positive or negative infinities, and then I'll give you a number like this that's the exponent is not that terribly difficult to calculate. Show me you understand how to do the mantissa, and produce the result. Okay. So addition, 1-bit adder, right? And so basically we're taking our XOR gates. Are you all familiar with 1-bit addition? 1-bit full adder? It becomes A and B, and so we have XOR here coming into the AND gate for C. So now A XOR B and C, or A and B is our carry bit, and our sum is A XOR B XOR C. So if I were designing this in Vhdl, what would I want to worry about? Yeah, so you already have XOR gates, you already have AND gates, you already have OR gates, right? So now it's just a matter of ensuring that your timing is correct. So if I were to briefly bring up my full adder. Oh, nope, cancel. Do not do that. And then it magically runs or doesn't run.
I swear this is the most expensive, crashy program.
Which you guys did not pay for, I should add, by the way.
Yeah.
So we can't really complain.
I found the free version.
I can complain.
So you have the full bit adder, right? So you add the components and or and XOR, right? And so I have 3 wire signals, and those wire signals come from your 1, 2, 3 wires, right? And so I add 3 buffer signals as well, just like this. And so gate 0 and gate 1 are the AND gate and OR gate, right? So I'm just mapping A to A, B to B, and wire 0 to wire 1. So in this case, it's just A to B, it's wire 0. Yes, I'm sorry, wire 0 is this one, and wire 1 is this one. So now I don't want this C input overrushing it, right? So what I want to do is I buffer the C input. I wish I could white it out just in time for you to take that photo. Oh. By the way, this is completely on the video, so you're going to win anyway.
Drawing, that's what I was doing. I wasn't doing it.
Well, no, the drawing's going to be on the video as well. No, I'm giving you grief. No, so now we've buffered it, right? So now our next level is going to be.
It's called efficiency.
I know. I'm giving you. I get to have fun with you. It's all right. So now we have our propagated signal, buff 0, and the output go into this XOR, which is what we've done here, right? And then if you notice, the exact same two signals go into this AND gate, right? So that's why the AND gate matches as well. So the thing is, we want to buffer this signal here, right? Because we don't want it overrunning these two AND gates. So that becomes this buffer. So I'm going to change one thing really quick. It's going to be the exact same layout, but I wanted to make sense why I'm adding the buffers where I'm adding them. So now, after that, we have our last thing, which is our OR gate, right? So we have 5 nanosecond delay calculated into the OR gate. And so now I'm buffering the sum bit by 5 nanoseconds, right? And that is what we did here. And so I'll be expecting you guys to do what I just did. And here's the output calculation. So now you can see why we do this wait 100 nanoseconds, because when you do these wires, sometimes you're going to get these unknown values starting out. So you want to ensure, then this is why when you're starting up your computer, there's this whole process where you can't just immediately start using the program. At the architecture level, it has to ensure that all of the hardware is properly instantiated before you can properly load things into the memory, before you can load it into the data path. So in this case, it matches our sum and cout values.
So today, let's say, what was the new architecture? Let's just go with an Ivy bridge.
Okay.
What's the general startup time for one of those CPUs disregarding hard drive you have, like an SSD?
I don't know the exact answer to that question. That's a good question. I'll look into it. But they're typically faster because they're not only have optimization at the hardware level, but they're optimizing the startup time of the boot. Basically, that program that you start is called a bootstrap program. For those of you who haven't taken operating systems, you load up the program into the operating system that specifically starts the computer. So there's people who it's their job is to do optimization of bootstrap programs because it's very important. So I don't know the exact answer to your question, but that's the concept behind it.
Did you say it's in nano or pico?
Oh, nano. Yeah. Just because you're doing so many tasks at once.
So pico is definitely kind of a question for.
Oh, you mean clock rate? Yeah, we're not at because nanoseconds is gigahertz. So we're still, like, the computers that you have right now are 2 gigahertz.
So the next is.
Yeah, so you need to be getting down to terahertz after that, which we haven't accomplished yet. If you can do that, we'll split the money and then get the heck out of here, right? You can start your own frat where you can do whatever you want.
It'll be called dude.
All right, so in the meantime, we're going to study subtraction. So normally you'd have to do a full subtractor. So let's say I want to derive an arithmetic logic unit that did addition and subtraction, right? Before, if you're just designing one, you have to design a full subtractor and use a multiplexer, right? Which requires a lot of overhead. So I'm going to show you how you reduce this using kind of the idea of flipping the bits like we did in 2's complement. So first thing we're going to do, in order to physically implement 2's complement subtraction in MIPS, you take, so it's going to be A minus B, right? What we're going to do is we're going to flip if you flip all of the bits, it just becomes A negated B, right? So if this works at 1 bit, this works at 32 bits. You just flip all the bits. So that's the first step. Convert all the values of B. Then, in order to obtain the 2's complement, remember we have to add 1 to that bit, right? But here's the thing. If you use that 1, it's the same thing as providing a carry bit. So remember, we're having the it carry in and carry out. In subtraction, it's borrow in and borrow out, right? So this just becomes the definition of the 2's complement, which is equivalent to A minus B. So in order to do that, you just, at the compiler level, since it's a compiler-driven encoding of the micro engine, we just flip all the bits, add 1, and then load it in there and just perform addition. So the way you can do that physically, as a 4-bit level, is to have an add sub bit, because you want to flip the value, right? So if it's 0, that means we want addition. That means we want the bit to stay the same. If it's 1, we perform an XOR. So if it's 1, it'll change it to 0. If it's 1 XOR 1 is 0. If it's 1, 0, it'll change it to 1 because 1 XOR 0 is 1. Does that make sense? And here's how we do it physically. We flip every B bit with an XOR bit, and then we just use a full adder. So instead of having a full adder and a full subtractor and a multiplexer, just add 1 XOR gate to every single bit. And this should see 3.9, not 3.10. So, doing this at the Vhdl level. So this is my Vhdl code that I did for a 4-bit add subtractor circuit. That's the test bench. So same thing. I have 3 STD logic vectors, 3 down to 0, 3 down to 0. I have a component and an XOR gate. So, and I did all these wires. I'll ask you that question in a second. So what I did is I showed you this last class, right, about how I developed this timing diagram. Right, so I know that the XOR gate's 5 nanoseconds, right? And then I do map it to the wire. I know that based on my design, if we go all the way up back to the XOR gate, so this took 5 nanoseconds, right, this stage? This took 5 nanoseconds, and this took 5 nanoseconds. So I know that if I make sure it's timed properly, the delay on my full adder is going to be 15 nanoseconds. So I have 15 nanoseconds. If I know this is 5 nanoseconds, then I'm going to want this to reach at 5 nanoseconds. I want all the inputs to arrive at each element at the same time, and I want all the outputs to come out at the same time. That's the timing constraint. So here, I have this bit go immediately to all the XOR gates, right? And then I delay this by 5 nanoseconds, and this becomes 15 nanoseconds. So now this output comes out at 20 nanoseconds like I have here. So this is also going to come out at 20 nanoseconds, which means I want these to come out at 20 nanoseconds, right? Buffers of, so this is 5 plus 15, because your XOR is always going to be 5 nanoseconds. So to do the second one, so I have all these commented so you can look back at it. 5 XOR plus 15 for full adder 0, right? And then gate 3, full adder XOR gate. Yes?
Could you scroll over all the way just so we get the whole thing?
Yeah. Does that make sense? So this was the initial one, and this was the second one. So let me ask you this question, because what I'm going to ask you to do, since we're building up towards MIPS, I'll show you that trick in a second. But since we're building up towards MIPS, I'm asking you to do a 32-bit version of this. Man, wouldn't it? Boy, it sure would suck if I expected you to do this for 32 bits, right? So let me ask you a question. Since you are logical engineering aspirants, how could I could even reduce the amount of code to do this. How could I use my previously used primitive blocks in order to maintain the integrity of the timing, but reduce the amount of code you have to do? There you go. So in this case, what I could do is I could build a 2-bit adder, and then have 2-bit adder, 2-bit adder, and instead of having to worry about all of these, how to code each XOR gate, I could just delay. You see how I have to delay the inputs here? I would just delay the inputs to the next 2-input adder. Then now you have a 4-input adder, right? Now what can I do with that? I can build an 8-bit adder, build a 16-bit adder, then I can build a 32-bit adder. So instead of having to code every XOR gate, every full adder in there, use the code reuse well, then all you have to do is worry about proper buffering. So the point of this is to show you that I kind of front loaded the work, and now you're putting pieces together.
Is there a way to do the buffering?
Yeah. So what I did here in the code is that here in this full bit adder, so this is my output of the XOR gate, right? And I also need to delay the input to A 5 nanoseconds, right? So going back here, I delay the input by 5 nanoseconds to make sure that this came out. So the way you do that in Vhdl is to go wire A0 is from A0 after 5 nanoseconds. So then, as you can see, I kind of increased the time to make sure they all mapped. And so you see how these are going down? The reason why it's going down, and then the last one, I'm just mapping the last output here without any delay, is because this is added first. So this is but I want them all to come out at the same time, right? So this is going to be the last one. This one comes at 65 nanoseconds because this is 5 plus 15 is 20, plus 15 is 35, plus 15 is 50, plus 15 is 65, right? So this one's coming out at the same time. Since this one's coming out at 50 nanoseconds, right? For those of you in the back, they'll scroll up a little bit. This one's coming out at 50 nanoseconds. I want to delay it by 15 nanoseconds to ensure it maps. So the way I did that in the code, full bit adder PhD. Oh yeah, I gotta scroll over here. See, I had to delay it by 15 nanoseconds. So I did the wire S2 maps to S2 after 15 nanoseconds. That's what I did there. And then same thing here, 30 nanoseconds. I call this wire S1 because it maps to S1, right? Does that make sense why I did that? So then wire 0 has to wait 45 seconds because this one comes out, this one is going to get there 15 seconds earlier, so I delay it by 15 nanoseconds, right? This one's going to come out at 35 as opposed to 65, so I delay it 30 nanoseconds. And this one comes out at 20, and since I wanted to come over at 65, I delay it 45 nanoseconds. So going back to the code, I can do that. So what you would do if we wanted to reduce this, I would do this, and then just put two full adders together where you're just controlling the timing of the inputs and the outputs to make sure they match. So if I was doing a 32-bit value, so we could actually do the quick math. It's going to be, each one's going to be 20, it's going to be 5 plus 32 times 15. So that's going to be our last value. So each one's going to subtract 15 the amount of delay. Instead of having to do that for each bit, you just do 2 to 4, then 8, so then you can just see how they all work out. Then you're building the 8 bits to make sure it's 16, and so forth. So that way, instead of having to design what I did here, I actually made this deliberately complicated to show you how to then tell you, here's a better way to do it. Because if you're not taught it, then you're in the lab doing this for hours and hours on end when you don't have to. Does that make sense? Okay.
Is that supposed to be A1?
Which one?
No, on the Word document. Second.
Yeah.
Yeah.
A0, B0, wire 0, A1. That should be A1, yeah. Oh yeah. Yeah. No, that's just mislabeled.
Yeah. So.
Okay, so I wanted to show you guys a little trick you can use in your test bench. So now we're starting to get to the point where you're building up a lot of values. And if I had two 4-bit adders, I can get up to 16 possible combinations, right? So here, at the top of any of these elements, so to my actual test bench, I included this line, use IEEE logic, STD logic, undersign.all. And that allows me to do this, for loops, down here, right? So in my simulation process, I initiate A and B. And since A and B are vectors, you can use quotes and then use the single quotes for AS since it's one signal, since it just adds sub. And then I can loop up from 0 to 15 for I. As long as these two don't match any of your variable names, you can do whatever you want with those. So, and then as it adds, you're incrementing b by 1. So it starts at 0, 0, then it becomes 0, 1, and then loops all the way to 15. And then the next loop, it's going to add a. So it's going to, as we talked about before, where if you add 1, 1, 1, 1, and add 1, it just becomes 0, 0, 0, 0 again. So now you're getting this instance where it just keeps looping and looping and looping. So here, I change it to AS as 1, and I did the same loop, right? In my notes, I actually showed you a more simple way to do it. So this is with just the B loop. So what happens is so you see how you add 1 here, so B is just equal to 1, and then A is counting. And so you see after the delay of 65 nanoseconds, it's just added, right? And then what happens is you get 1, 1, it becomes 0, 0, 0, 0, like we said before, but now you get a carry bit. And then it restarts again. So now we're down to 0, 0, and 0, 1, so the carry bit goes away. So it's properly simulated. So here I added the B inside the loop to show you what happens. So now we get carry out, but now the carry outs go longer and longer because we're covering more and more. So, and then from here, I changed I started AS to 0, so I added a third loop around there for H in 0 to 1 loop. And then after the first loop, it changes it from A is 0 to A is 1, and then does all the calculations again and comes out. And so that becomes the simulation right there. I think I've done 3. Yeah, I need to go through and fix the VH. Don't worry about the VHDL assignments. Worry about your exam through Tuesday. And I'm gonna take your feedback from your submissions and figure out. I'm gonna actually do a optional lecture on YouTube based on your feedback to try to show you guys improvements and things that you guys were struggling with. So, but I think this one was actually the same one as 3.2. Okay, so this is kind of what I was alluding to. If full adders, they kind of cascade like this. This is what's known as a ripple carry adder. And that's what you're going to be designing your VHDL because it's the simplest of the adders we're going to discuss right now. So you guys are just carry in, carry out, carry in, carry out, and so forth, all the way down to 32 bits. But if you want to speed it up, what you can do is you can have a 16-bit ripple carry adder, and then you have 2 additional ripple carry adders here where you're bits 31 through 16 go into both of them for A and B. And you initialize the carry in bit. This one is 0, and this one is 1. Right? So what happens is it does the calculations at the same time as the initial carry adder, and you're going to have, since you can only be a 0 or a 1 from here, this would normally just go to the ripple carry adder, and you have to wait for all these calculations. Because of this, we can actually have the 2 possible solutions it could be, and use the carry out as a multiplexer to give us our remaining sum bits. And then it would also be propagated as the final carry out bit. So that's how you can speed it up. Now, some of you are probably thinking, okay, we could break this down into 4 bits and so forth. And the more you break it down, the more wiring you have, the more multiplexing you have. And so that's known as a carry select. And then if you're breaking it down further, you eventually have to do this thing called carry look ahead. Now, carry look aheads have the best execution time. All of you know big O notation, right? And nobody, what's that? Just learned it? Okay, good. So big O of n is the slowest execution time for ripple carry, but is the lowest amount of space. Carry select, big O root of n for time, but requires more space. Big O 3/2 of n, so those of you notation, it's essentially equivalent. So it's a little more, but it's not exponentially more. And then carry look ahead requires big O of log n time for optimal, but it requires n times log n for space complexity. because it requires a lot more decision logic.
Could you wait on the sir?
Okay. All right. So from here, we can build arithmetic logic units. We have the calculations. We've done full adding, right? And so if we wanted to do an arithmetic logic unit that calculates NOR, OR, and AND, you can just build 1-bit ALUs that produce the results. You can do it in other ways. You can actually, if you're thinking about, okay, I want to build an efficient ALU where I'm doing with an adder. So we've got an adder, we've done the 2-bit adder, done the 4-bit adder, done the 8-bit adder, done the 16-bit adder, right? And you calculate all this out. What you can then do is you have the 32-bit values, right? So then you can start saying, well, a 32-bit value for a full adder, a 32-bit value for NOR, which is just A, NOR, B for all of the bits. And then I use my multiplexers. I use some combination of my 64 to 32-bit multiplexers to decide between all of them using logic. So that's how you build these pieces toward all these pieces. Now the ALU should just proper buffering and timing becomes much easier to code, right? So that's how this would be done. Additionally, for arithmetic logic unit, we want to worry about something called comparators. So it's actually a physical circuit that compares 2 bits and tells you whether it's less than, greater than, or equal to each other, right? And so this is a 1-bit comparator, and the logic on the output is C is A not B, right? So if it's true, that means A is 0 and B is 1, which means that A must be less than B, right? If D is X NOR, right, which means they're the same. And then E is A B bar, which means that A, which for it to be true, A has to be 1 and B has to be 0, which means that you have comparator values for A greater than B. So showing you this as a point of comparison, this becomes the complicated process for actually designing a 2-to-1 comparator, right? I'm sorry, so this is a 2-bit, so this is a 1-bit comparator. So if you had to do this for every single time without cascading, this is a 2-bit comparator. So you can see it becomes pretty complicated pretty fast. If you were to do a 4-bit, 8-bit, like a 32-bit MIPS, that would become complicated. So to spare you the trouble, this is the 32-bit ALU. This is the 2-bit comparator. And you want to build this because what you can do is you can use these 2-bit comparators to cascade, use 2-bit comparators in series in order to actually build up towards 32-bit comparators. And you would do it in this way. So here we have A1 and A0. We have these set of AND gates. This would be A1 and B A0 and B0 not. Then these are all the conditions where we determine that A is greater than B. We have all these A is less than B. And in this case, what we've done is we've done a reduced version where we calculate A equals B and A greater than B. And instead of having an additional circuit that calculates A less than B, what we've done here is just use a NOR gate. So if it's not A equals B or A greater than B, it must be A less than B, right? So this is a little design method that we've used to reduce the area of the 2-bit comparator. Now, in order to do subsequent comparators, you have A1 and A0, B1 and B0. So you can start out with these bits right here. So they're carrying A is less than B, A equals B, A greater than 3. And
What chapter is this in the book?
this is chapter 3 in the book.
Is that indices?
Yes. So based on that, you have these set as 0. now we can cascade it further. Because when you're talking about anything with a comparator or anything with a multiplexer, the analogy that I gave to some people in the lab is thinking of it like it's a basketball tournament. So, 32-team basketball tournament, right? So we select 0 or 1. If you lose, you're 0, you don't pass. If you win, you're 1, you pass on, right? So use a multiplexer to take it from 32 to 16, right? So then the same thing, 16, 0 to 1, multiplex down to 8, down to 4, down to 2, down to national champion. The comparator does the same thing. You have these two, so let's say we had to do like 1, 0, and the rest are all 1s. So we know that the most significant bit is different, but all the rest are the same. So we're going out, we're comparing this bit's the same, 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 all the way up to the top. Or you do this, the most significant bit is greater than the next significant bit. Well, if it's already done, we don't need to compare the rest of them, right? So we're going to start like this, and what's going to happen is start the most significant bit. If they're the same, then you go down to the next one. You go down to the next one, and so, right? So you can use loop in your Vhdl, or you can use structural Vhdl to accomplish that. Right? So we are almost at the end of class. So let's do. It's going to be 3.7 through 3.14, and it was example 3.1, right? So that is due next Thursday.
You say 3.14?
Yeah, it's going to be homework. It's going to be example 3. TGO's 3.7 through 3.14, and example 3.1. Due next Thursday.
So what you end up with, we're just going to look at the first 4. So it's going to be 1 plus the 0.